I come from la Universidad de los Andes in Colombia, that university over there. This one over here. You know, if you're ever down, just let me know. I'll be happy to go around. But I'm also here. I'm with two hats. I have a startup that's called Cinterest over here. That came from some of my work in the PhD, and it does have a relation with the talk I'm going to talk with what I'm going to talk about. And this is where it came from. That RIT, that's where I did my PhD. So yeah. So I'm going to talk about biochar-based composites, a little bit understanding their potentials and their limitations. So first, acknowledging that the biochar journey is awesome and it's continuing to be awesome. The production has come such a long way. We're now talking about thousands of metric tons. We're talking about some very exciting numbers that sound like a really scale. But research also has come a long way. This is the paper from a colleague that she's also Colombian from Washington State University that was published this year. That we're starting to be able to simulate and understand the process of pyrolysis enough to predict fairly okay properties like surface area, porosity, nutrient availability. So that kind of things are starting to be able to be simulated, and that is also a very exciting part because it allows us to think even in higher ways. But today I'm going to talk about a little bit about one of the industrial applications of biochar, thinking about the industrial end market of plastic composites. Why I think it's interesting to talk about this. Industrial end markets can be drivers of biochar production, of biochar adoption. They can be the ones that pass from one day to the other and multiply by a factor of 10 world production. We just need some of them to be like, okay, I'll try this. And that's because those markets are just huge. That kind of investment in their part is not that significant, let's say, in that sense. So they can stimulate the growth of biochar. They can, and it's good also for the biochar industry because it diversifies the end market. So we don't depend on one end market if something happens. It makes less risky also for investors. Investment looks that, there's different end markets that the biochar is going, of course, they're going to feel more confident. And it also valorizes the biochar not only for the carbon that it has, that's what CDR does, but it also valorizes for the properties this material has. This material is pretty amazing. It's very porous. We can play a lot around the surface properties. We can play a lot. We can modify it to be an engineering material. So it's really worth thinking about it as a very specific and special material, more than just the carbon that it sequesters. And, to understand these markets, we have to understand the volumes they're going to represent. So if we think about the medium-sized cement plant, just a medium one produces around 350,000 tons a year. Medium-sized plastic transformer is something around tens of thousands of tons a year, and filter manufacturers around 3,000 tons a year. So you think, okay, I'm gonna promote a cement that is 20% biochar, and then you look at that number and you say, oh, who's gonna make that biochar? Well, I'm gonna need a lot of biochar to supply. And what happens when you try to supply industry? You have to understand that they play by games that usually don't have the flexibility we would like them to have, right? So low or equal cost is usually a rule that we have all to abide, and it's a complicated rule, especially if you're thinking about the construction industry, you're thinking about the plastic industry. You have to compete, the additives you're competing with. For example, calcium carbonate that we're going to talk a little bit about ahead. Calcium carbonate is cheap. It's very, very cheap. You can buy tons of it with not a lot of money. So you are competing against a very low cost. And you cannot play around too much with the functionality of the product. You really have to think about what is my biochar going to do in that composite? What is the role I'm going to play? And in the plastic composite realm, that's a little bit where I feel more comfortable, because that was some of the thematic of my PhD that Kathleen was involved. I played a lot with the plastic films. And in plastic films, the thinner you are, the better you are, right? And the problem is that biochar don't disperses very well in polymer matrices because of particle size, compared to, say, carbon black. Carbon black, it's a nanometric material, and biochar is just not. So you're gonna have, in thin plastic films, you're going to need, if you want to use biochar, you're going to need a thicker film, and that will just hinder the economics and the environmental dynamic of your film. So it's a sad conclusion that biochar just actually forces you to, so you can have the same functionality, it forces you to have a slightly thicker film, and that additional plastic makes it more complicated. So if we focus on thicker composites, so say injection molded plastics, right? And with the right match of feedstocks, so this sorry, I didn't talk about. This is where you see the dispersion difference. This is a biochar where, based on the thickness, this is the amount of biochar you need to get a certain opacity, and this is the amount of carbon black. So you see the difference in dispersion based on the particle size. What happened? In agricultural mulch films, that was the thematic of this paper in particular, you need a certain opacity so the mulch film does its job, right? You need to be opaque. Otherwise, plants grow and you did nothing. So you need an opacity, a minimum opacity, so you need a minimum amount of biochar for your film to be functional. And that hindered the environmental impact, because you need a thicker film, you hinder the environmental impact. So you really have to think about, when thinking about biochar and composite, you have to think about thicker. So say this plastic cup, that's a thick plastic. It's more than 100 microns thick, so it's okay. And you go in literature and you find people talking about 50%, 60% biochar. So what does that mean about the environmental impact and the economics, right? Our God, because here we're all biochar fans, and I'm one of the biggest, I think, it's going to be better for the environment. So to answer that question, I'm going to do a life cycle assessment, thinking about the whole life, right? I'm going to talk a little bit about that, but I'm going to do a cradle to gate. So I'm going to stop right here before the use, because I'm going to assume once I get my plastic, my injection molded plastic out in the market, the use is going to be the same, and there's not going to be any difference between a biochar composite and the other one. And so I'm going to account for all emissions to water, air, and soil during this process, and I'm going to try to translate that to the ultimate risk, right? There's standards for this, we have to follow them, and those standards say you need a goal and scope, meaning I have to explicitly tell you why am I doing this and what is the scope of my life cycle assessment, right? The boundaries. I am going to tell you what is my functional unit, and that's a very important part. And the impact assessment methods, right? What is the data I'm using and how am I making that, and the life cycle impact assessment methods that I'm using for that. And what is the sensitivity analysis to show the robustness of my conclusions, right? That's how you do a life cycle assessment. You have to follow the standard. And so it's an iterative project, and today I'm here showing some preliminary results that I made. So the goal and scope is to understand the environmental and economical, but right now environmental implications of using a biochar master batch for injection molded plastics. And my inventory, I'm going to explain it right here, and the methods I'm using as well. So I'm going to do a cradle to gate, as I already mentioned. The boundaries of my system are therefore at the end here when I make the injection molded plastic. Once I make, say, I don't know, the bucket or the tray, whatever. Everything is injection molded. After a while, you see it all as the same. But what my functional unit is, and I want to clarify it, is a set volume of injection molded plastic. Why? Because if you get into nits and grits, biochar composites have different densities than other composites. Therefore, you cannot talk about a specific weight. It makes it harder. So actually, I'm going to talk about the set volume, because that's in injection molding. Your mold has always the same volume. So that's the one I'm going to use. And I'm going to use the amount of plastic I need to fill that volume. So that is my functional unit and the goal and the scope. Now, what is the data I'm using? So I'm using, because of the sensitivity analysis, I'm using two different sources to model my biochar production. This one is for a purpose-grown biochar. It's a good reference, very recommended. They do a very comprehensive LCA of that. And with this one, I'm gonna take account the waste stream. In this situation, they do sludge, but it can be any waste. And then for carbon black and calcium carbonate, I use the EcoInvent one. EcoInvent is a very big database in life cycle assessment that usually is very good for Europe and United States. For the others, they have us a little bit forgotten, but it's okay. And I want to manufacture my injection molded plastics in Rochester, New York. So I'm going to bring my carbon black from Hamilton, Ontario, Canada, which is the closest manufacturer of carbon black. I'm going to bring my high density polyethylene from the ExxonMobil Houston, Texas plant, and I'm going to do it by train. That's when you have a big plant, you bring your plastic by train. The transport is therefore with the EcoInvent and the extrusion as well, right? And so that's my data. What are the methods I'm using? So because I'm using purpose-grown biochar, the CO2 uptake is a little bit tricky. Basically, there's some impact. So the classic one, recipe, is usually what is used a lot to talk about the impacts. And the problem with that one is that they don't account for CO2 uptake. So I wanted to account for CO2 uptake, right? Because I'm growing trees to put in the biochar, to make biochar with, actually the bark. And so for that, I used specifically the IPCC that includes CO2 uptake. So all the global warming numbers that you're going to see are calculated with this method, and all the rest, 16 impacts, are calculated with the recipe. And everything is modeled in the CIMA Pro software, which is the golden standard in life cycle assessment. There are other softwares, and we can talk a little bit more about the details and nits and grits of that, but usually people use CIMA Pro, but yeah. And the sensitivity analysis, so again, this is an iterative process, and these are preliminary results, but the sensitivity analysis were on the amount of biochar that I'm going to put in this set volume. So I'm gonna explore 10, 20, and 30% biochar composites, and I'm gonna end the sourcing. So this is purpose grown, that I'm using the bark to make biochar, because from talking with people, I've learned that that's the nicest thing to make the most fancy biochar with the fanciest amount of carbon, et cetera, et cetera. So I've heard of projects that look for, grow biochar, and this is from a waste stream. So what did we find? So first, the master batch. So when you make injection molded, you first do a master batch that is usually 50-50, and then you take that and you put it in the injection molder with more plastic to get the density you want. And so we got, it was pretty much what we expected. So if we looked at the global warming potential, we're going to find that the master batch of biochar is way less rough on the warming potential than the others. Then the calcium carbonate and the carbon black. I hope you see the colors. But biochar because of the nature of forestry, and that is in that LCA. There's a little bit more emissions in certain things, but I want to point out that in purpose-grown biochar, you have the land use impact is fairly intense, of course. But we have to think not that's the master batch, right? And the problem is we want to talk about functionality. So the amount of biochar you need in your composite is not always the same, right? So we're going to compare functionality. And carbon black, the magic of carbon black is you need very little. So I'm going to have to compare 1% carbon black composite to a 10% biochar. So they have more or less the same darkness, and that is very important for the industrial. And I'm going to compare the filler application, that is calcium carbonate, versus biochar, so 10%, 10%. And when we look at that, then the story is not that exciting. Sadly, I have to tell the not exciting story that we have maybe a 5% improvement in our life cycle assessment of my biochar composite at 10% versus a carbon black that is just, why? Because the impact is driven by the plastic, right? Biochar of course helps, but it's not it's so much plastic. So the plastic is the driver of the impact, and that's what we have to understand, that we cannot offset that impact with only biochar. So as you can see here with the color scales that hopefully you can see, I don't know if you can see it, I barely see it, but here you can see all of this is the plastic, and this is the biochar. So the master batch is way smaller. But again, the land use one is an important that we see that our composite is having way worse impact in land use because it's purpose grown. So what happens now if we increase the amount of biochar, say 30%? Of course, we see an improvement in the global warming potential up to 20% less. But I mean, we have to take in account the other ones. The land use is out of control. The ozone formation, I think that's very specific to the paper that I'm modeling, so I have to say it. But the land use is the one I'm pointing the most of it. So the conclusion is we improve a little bit here, up to 20% less greenhouse global warming potential, but there are other impacts that we have to talk about and we have to think about. And here is, I think, the point that what happens if we change our biochar for not a purpose grown, but a waste feedstock in the industrial setting, right? And so, as you can see, so this is the lighter green, which is going to be in the left. So it's basically, it's the same global warming potential as the carbon black, right? But when we look at all the other impacts, it's way better. I mean, look at the land use. We improved in all the others, right? So purpose-grown biochar is going to actually hinder a little bit the story. And clearly, we cannot promise a carbon net zero plastic because the plastic composite, it's driven by the impact is driven by the plastic, and the biochar cannot offset that. So we see clearly an improvement in most of the things, and in the land use, we control it with the waste feedstock. So what can we conclude about it is that we have to think about the trade-offs when we think of on a grown biochar versus a waste feedstock biochar. I think waste feedstocks make a lot of sense also because, right, we're avoiding emissions and other things. We should not commit to carbon net zero plastics because it really doesn't appear that it's feasible with the traditional and industrial methods of manufacturing. We have to think about all the different things like the matrix, the polymeric matrix. We have to think about the additives. We have to, the whole thing to be able to try to push something. So with that, I want to thank you very much. I recommend you the waste feedstock talk about biochar with Tom in an hour. And yeah, any questions I would be happy to answer. Sorry about that.